our YouTube and make sure the live streaming looks good? It should be good because it's coming up. It's not streaming.
Seems good.
Raph, can you help me troubleshoot real fast?
You know, there's an eclipse of the moon in a few days' time.
It's not showing the. So I've got it streaming, and it's not showing up here.
Can I see what's on OBS?
Yeah.
It looks like it's going.
That's pretty delayed.
Is it going? Oh, good.
Yeah.
Well, there's going to be a delay. There's going to be a delay. It's always about 10 to 20 seconds
Well,
delay.
it's more. It's
Can I see this or
See what?
your internet connection? I would try and maybe ask if you can get on their actual Wi-Fi because that might be a better connection. But
I think we might just be far away from the building.
yeah, I would try and also just close out of everything else using internet, which can help as much as you can.
Right. Mm-hmm.
Never hurts.
Okay. Well, I just closed YouTube, so I hope it's
Because
okay.
this is telling you your rate,
Yeah, it's pretty bad.
which is not amazing, but yeah, trying a different.
Honestly, as long as audio is fine, it's not like your slides. Do you have videos in your slides?
I mean, not ones that are that important.
As long as audio is okay.
Oops.
Maybe close. Yeah, it's closing Zoom.
Yeah.
You can actually. So okay, here's what you can do. So if you go to stream settings, you should be able to. What I would say is try and lower the. So a stream or output.
I'm in the same boat. I have 3 times this week alone.
Go back to stream. Sorry, or click video. So
It doesn't let me.
It won't let you do it while the stream's active.
Yeah.
But if you can stop the stream, just click.
That's fine.
I think that's better,
Okay.
and hopefully that gets you within your. Yeah. Again, that's the kind of things you want to adjust. So maybe now it might be a little bit better, but again,
Yeah, as long as people can hear and like see the static slide.
Are there people on the stream?
I am not sure.
It should tell
3
you.
viewers. Assuming 2 of those are us. I don't know what
Alright.
the other one is.
Well, okay then. Okay, let me get my scripts.
And then I need to track you guys very closely.
Get my scripts.
Are you live tweeting?
Yeah. I gotta sit somewhere where I can take the. You're on the same Wi-Fi, right?
Yeah, I'm on the guest one, yeah.
Is the link on the Facebook page?
It should be in the event.
Hello. How's the audio sound? Can you hear me?
Yeah.
In the back, can you hear me? Okay. Not too much noise on. Hi, welcome to SpaceDrafts number 70, our James Webb Space Telescope special. My name is Logan. I'm going to be your host for tonight. I am a graduate student here at the University of Arizona. And so I just want to welcome you to SpaceDrafts. We are part of Astronomy on Tap, which is a worldwide organization that is a network of shows that meet in local venues all over the world.
Yeah.
So if you know someone, or if you're not from around here, there's probably one near you wherever you're from. Tonight is our James Webb special in celebration of the launch of the James Webb Space Telescope next month, December 18th. To get you excited about that, we have some special speakers, local speakers here from the University of Arizona who are experts in the James Webb Telescope and helped produce this thing that we're all really excited about. So just to give you a little update on how it's going to work here before we get started. So there will be a trivia question at some point during each of the talks. When you think you know the answer, please throw your hand in the air, and someone will call on you. And if you get it right, you could win a wonderful SpaceDrafts sticker. Woo! Thank you. If you don't win, never fear. We are selling the stickers for $2. And your proceeds go towards enabling us to buy even more cool merch to support the show. So please consider lending us your $2 so we can continue to bring you even more cool, exciting merch and SpaceDrafts talk. Tonight we will have telescopes on site. They are out towards the train yard and somewhere over there. I'm not 100% sure where, but they're out there. During intermission and after the show, please feel free to head over and check out whatever they're looking at. The moon is up and very nice. I think they were looking at Jupiter and Saturn. I think are over there. So definitely head out and check it out. The telescopes are brought to you by the University of Arizona Undergrad Astronomy Club. So please thank them for volunteering their time and enjoy whatever they're looking at. Finally, we have a little tradition here at SpaceDrafts. We are right next to an active train line, and sometimes that train likes to interrupt our talks. And so when the train is coming and you can't quite hear, we like to give a little choo-choo, raise our glasses, salute the train, and take a sip. So please don't be annoyed when the train comes by. Just use it as an opportunity to take a sip of your beer. Okay, so that's all for me right now. So first up, we're going to hear from two graduate students here at the University of Arizona, Charity Woodrum and Raphael Hviding, and they're going to tell you about the cool science that James Webb will be doing. So give it up and welcome our first speakers.
Hello, thank you all for having us. We're really excited to be here. So first I just wanted to start out with a question. So how many people here have ever looked up at the night sky and wondered about your place in the universe?
Woo!
Okay, yeah, there's a lot of you. That's because it's a shared human experience, and since the beginning of humanity, we've been looking up at the night sky and wondering about these fundamental questions, like how did we get here and are we alone? And the pursuit to answer these questions, these fundamental questions, is what drove us to build the James Webb Space Telescope.
So the James Webb Space Telescope, or JWST, is NASA's great big flagship mission. You can think of it as a successor to the Hubble Space Telescope. It's actually in the background of our first slide here. We can actually get a little bit of a better look at it right there. And this is an artist's depiction of what James Webb will look like after launch. And we're today going to be talking about the next generation science that we're going to be doing with the JWST.
Not only will you be hearing about next generation science, but you'll be hearing about it from next generation scientists. This is Raphael Hviding, and my name is Charity Woodrum, and we're both graduate students at the University of Arizona getting our PhD in astronomy and astrophysics. And we also work for the JWST science team. And that's because our advisor is Marcia Rieke, who's the principal investigator for the main camera on JWST. And she'll be speaking later about, how JWST was built and how it works.
And right now we're going to be mainly focusing on the amazing science that JWST will enable. And one of the unique things about James Webb that allows it to do such revolutionary science is the fact that it can see a kind of light that our eyes are actually not able to see. And this kind of light is called infrared light.
So this is a picture of the entire electromagnetic spectrum. I'm sure you've probably seen it before, but maybe it's been a while. So in the center is visible light, where you can see the rainbow, and to the right of that is infrared light, and that's what JWST will be able to see. And it's basically just a lower energy form of light.
And so you might be asking yourself, why is the infrared so important? Why is studying infrared light so important that we would dedicate a flagship NASA mission to studying it? And today, that's actually what we're going to be talking through, the four main science objectives and areas of the James Webb, relating those specifically to this unique feature of this telescope.
So first we'll be discussing other worlds, or planets other than our own Earth.
We'll then be talking about the life cycles of stars. So that's how stars are born, how they live, and then ultimately how they die.
We'll also be talking about galaxies over time, so how they form and how they evolve.
And then finally, we'll be talking about one of the main reasons that the James Webb was built in the first place, and it's to study what we might call the early universe, to actually see the first galaxies ever being born.
So yeah, first we'll talk about other worlds. This is a picture of our own world, planet Earth. And to understand how we got here, we like to study other worlds. So that means planets that are in our own solar system, as well as planets that orbit stars other than our own sun, and we call those exoplanets.
Now, we'll be starting just in our own backyard with the planet Jupiter. Now, Jupiter is the biggest planet in our solar system, and I'm sure it's something the telescopes right out there by the training yard will be taking a look at tonight, so definitely go take a look. And this is what Jupiter might look like if you had probably the best telescope on Earth. And you can see some distinctive features that you might be able to see maybe tonight, specifically these bands across the front of the planet, and also that famous giant red spot.
But again, JWST will be seeing an infrared light, and here is planet Jupiter in the infrared. So you can see it gives us a completely different view of the planet.
Yeah, sections on this old planet, you know, the Jupiter with visible light, they used to be dark, but now they turn bright when we switch to the infrared. And this new view of the planet allows us to maybe learn something new about what's going on there. For example, one thing that we actually don't know for sure about Jupiter is why the red spot is red. We have some ideas, but we believe that James Webb might actually be able to shed light on questions just like that.
Next, with JWST, we'll be able to see planets being born. So what you're seeing here is an artist's depiction of a solar system, or of a planetary system being born. So in the middle is the star, and there's this disk around it, this debris disk, and that's made up of dust. And the new planets will be formed from this debris disk. So this is what our solar system may have looked like when it was quite young. And JWST will be able to see other planetary systems being born in the universe.
But turning our attention to our own solar system where planets have been born, we can actually see that a few planets live in this sort of green zone here. This is a zone that we call the Goldilocks zone or the habitable zone, which we might describe as a place where liquid water can exist on the surface of the planet, just like we actually have here on Earth.
Maybe not in Tucson. So this is an example of an exoplanetary system. So up until the 90s, we weren't sure if we were the only solar system in the whole universe. But now we've discovered that there's thousands of planets that are orbiting other stars. And these are some of those planets. This is called the TRAPPIST-1 system. And again, you can see the habitable zone in green around its own star. And you can see that there's a couple of planets within that habitable zone. So this is one of the primary targets for JWST.
And in fact, we won't only be studying, planets that might live in habitable zones around other stars. We'll be studying all sorts of planets, rocky planets like our own Earth, gas and ice giants like the planets in our own outer solar system, strewn all throughout the galaxy.
And one of the most exciting things about JWST is that it will be able to study the atmospheres of exoplanets. So in this image, you're seeing a picture of what it looks like when you spread out the light of the atmospheres within our own solar system to look for things like water and carbon dioxide, and JWST will be able to do this with exoplanets. So while we won't be able to know if those planets have life on them, we hope to see whether they have conditions that are favorable to life.
So to sort of summarize this other world section, our goal is almost to understand our own Earth, its past and potentially its own future. And we're going to be doing that with James Webb by
studying planets within our own solar system,
watching planets as they actually form,
finding exoplanets that are far away from home,
and potentially most excitingly, studying the composition and makeup of those exo-atmospheres. So next we're going to be talking about star life cycles, just like our own sun. So we all live, in the desert. We're pretty familiar with this star. We kind of feel it every day. One of the main objectives for the James Webb Space Telescope is to understand how stars are born, how they live, and how they die, which is kind of like our own sun here.
So this is an example of an interstellar cloud of gas and dust, and this cloud is collapsing, forming new stars. And this is what it looks like in visible light. Sorry, in optical light, not invisible, but yes, optical light.
But if we turn on our infrared glasses, we'll be able to get a different view of what this interstellar gas cloud looks like. We can actually see that light, infrared light from deeper within this cloud is able to escape and reach us. And so quite literally, we're able to peer deeper into this cloud. You see how we can see more stars, and it almost looks like there's less of that cloud there. So we're seeing deeper and actually getting a closer up look to this star formation.
This image is a very famous astronomy picture. It's called the Pillars of Creation, and it's an example of a stellar nursery. So a stellar nursery is exactly what it sounds like. It's a group of young stars that are all being born from the same cloud of gas and dust. And you can see the dust in this image. It's the dark spot that's obscuring light from behind it.
But if we again switch into the infrared view, we'll see hundreds, if not thousands of more background stars. We're able to basically peer through that dust and get basically, a deeper in view to watch those stars being born. And so by now you've probably figured out that all we're really doing here is getting an excuse to show you really beautiful pictures of things in space and then kind of showing you what they look like. And this is absolutely no exception. This is the Horsehead Nebula, another stellar nursery.
And when you switch to the infrared view, again, you can see into the dust cloud. So you can see the stars that are within the cloud.
So fast forwarding from the birthplaces of stars all the way to the end, to death, this is what you might expect to see from sort of a gravesite of a star. A star, very much like our own sun, might die like this, and that essentially entails releasing its gas and dust back into the universe to be recycled.
And this is what it looks like in the infrared view, and you can see much more structure with this view. So that can give us more idea into the physics behind how this process happens.
So, to understand the life cycles of stars, we want eventually to understand the sun that we orbit around, and so we're going to be using James Webb to
see gas clouds collapsing,
watch stars as they're being born,
peer into the heart of stellar nurseries,
and actually study the graves of these dead stars.
So now we're going to be talking about galaxies over time. So who here has seen the Milky Way at night? Okay, wow, yeah, a lot of people in Arizona. That's awesome. So this is a picture of our own Milky Way galaxy strewn across the sky. And a lot of people ask me about those dark spots. They want to know why there's no stars there. But that's actually not what's going on at all. There's actually just as many stars in those dark spots. However, there's a bunch of dust in between us and those stars. So this dust is blocking our view of the stars behind it.
But if again, we're going to turn on our infrared glasses and see what our galaxy might look like or looks like in the infrared, and we'll see that dust doesn't actually block starlight, but it glows incredibly brightly. And another way to maybe wrap our heads around this to get a better picture of what's going on here, it might be good to turn to one of our nearest galactic neighbors, the Andromeda Galaxy. The Andromeda Galaxy is a galaxy that's extraordinarily similar to the Milky Way. It's about the same size, it's about the same shape, and it even has those same dark lanes that we saw in our own Milky Way.
And this is a view of the Andromeda Galaxy in the infrared. And you can see again that the dust lanes all glow. And it turns out that dust is extremely important when you're studying galaxy evolution like I do, because gas and dust within galaxies is used as fuel to form new stars. So if you want to understand how galaxies evolve over time, you need to understand the properties of dust. So this is one of the biggest things I'm most excited for.
Now, one other way that galaxies can grow is actually by smashing into each other. And so this is a picture of the Whirlpool Galaxy and one close companion, and these two galaxies are actually interacting and eventually will hopefully merge. And this is what that process looks like if we take a look using our eyes or the optical wavelengths.
But when you switch to the infrared view, the Whirlpool Galaxy looks a lot different, and again you can see the dust more brightly and everything like that. And it's important to study these galaxies as they're interacting like this, because when they cross paths in this way, it can often cause a trigger of star formation. Very similar to how whenever I cross paths with Raphael here, he brightens my day.
That's very sweet of you to say. I would tip my hat, but I'll do the next best thing and just show the Sombrero Galaxy. This is a galaxy which is a fantastic example of a galaxy which we're pretty much seeing edge on.
And the most distinctive feature of the Sombrero Galaxy is that dust lane right through the disk. So you see that dark stripe across the galaxy. And in the center, you can see the bright starlight. Now, by now, we've shown you a lot of galaxies in optical light and in infrared light. So for that sticker, I want someone to raise their hand and tell me what you think will be the biggest difference between the optical image and the infrared image. What feature do you think is going to change the most? Does anybody want to give it a try? Other than another grad student, please.
That one over here?
Oh, yeah. Yes,
yeah,
exactly. So
The-
they said, the dark dust lane is going to be very bright, and that's exactly correct.
Yeah, so we're able to see that ring of dust around the galaxy much more clearly. So turning our view now to another galaxy known as M77, this galaxy might look kind of plain and unassuming in the optical. But what's going to be fascinating is when we again switch to the infrared. We're going to see that the galaxy pretty much entirely disappears and is replaced by something extraordinarily bright. Now what that tells us is that there is something very small in the center of this galaxy that is emitting so much energy and light that it's completely outshining its host galaxy in the infrared. And what we believe this to be is a supermassive black hole that is shredding material around it and releasing energy that might only be visible in the infrared. So to summarize our understanding of what we're going to learn about galaxies over time, the first thing that we're going to get is an idea of what galaxies look like in the infrared.
We'll also watch galaxies collide over cosmic time.
And we'll track the fuel sources of galaxies, that dust.
And JWST will be able to find these hidden monsters in our universe.
But now turning back the clock all the way to the beginning, we're going to be talking about the early universe and one of the main motivators for why the James Webb was built. So who here has heard of the Big Bang? That's a good number of people, right? It's how our universe started. But who here knows what came after the Big Bang, the so-called dark ages of the universe? A couple of hands, okay.
So the dark ages of the universe was this period in time about a couple 100,000 years after the Big Bang, and it was a period in time when the universe was completely dark until the first stars and the first galaxies started forming, and we think ended the dark ages.
We're now going to be flying through a simulation of the end of the dark ages. Now the dark ages were kind of dark for two reasons. The first, there weren't a lot of stars, and the second is that the universe was actually filled with opaque gas.
But as these stars started forming and more galaxies started forming, they emitted radiation which changed the gas around them and made the gas transparent.
So what we're seeing here is as we start with these sort of dark regions where light can't permeate the universe, and these regions where the first galaxies are being born, eroding the gas around them and creating these pockets of a transparent universe. And what we're going to be left with at the end of this is a universe that's transparent, which we kind of take for granted. The fact that you can see stars in the night sky at all is because the universe underwent this process and became transparent thanks to the first galaxies.
And so this is what the first galaxy looks like to us. Like, this is what a galaxy looks like to us in the dark ages. And you can't see anything there, right? It looks like there's no galaxy there.
Yeah, so these first galaxies are completely invisible to us, people who can only see in the visible portion of the electromagnetic spectrum. But if we go down to these lower energies, specifically by using the James Webb Space Telescope, here's a simulation of what we might be able to see. And we can see that that galaxy immediately pops into view once we're able to actually use the infrared light coming from these early galaxies.
And the reason that JWST will be able to see these first galaxies is because it's such a huge technological improvement over anything we've ever built before. So this is an image from the Spitzer Space Telescope, which is one of NASA's other infrared space telescopes.
Now this image you're seeing here on the left, it took about 25 hours of a long exposure to actually get this image. That's leaving your shutter open on your very expensive camera in space open for 25 hours. Now on the right, I'm going to show you what James Webb will be able to do, not in 25 hours, not in an hour, but in less than 20 minutes. This is the power of the James Webb Space Telescope, to see tens, hundreds, if not thousands of more galaxies at an incredibly improved resolution and clarity than anything that's come before.
Okay, now to summarize our early universe section.
Our goal is to view these first galaxies, to watch the first galaxies of the universe ever being born.
But the early universe is opaque to us.
But James Webb, thanks to the fact that it can see infrared light, can peer into the dark ages.
And it will fulfill its primary goal, which is to see the first galaxies that ever formed in our universe.
So that's an overview of the main areas that James Webb hopes to tackle in the next generation questions in astronomy. So we've talked about
other worlds like exoplanets that orbit other stars,
the life cycles of stars that might teach us something about our own sun,
how galaxies form and evolve over cosmic time.
And our goal to see the first galaxies in a dark universe right after the Big Bang. So I guess we could summarize our talk by saying, the future is infrared, the future is James Webb. Thank you so much for having us talk. The launch date for this telescope is December 18th. All we've done is talk about the science, not the amazing technical and engineering marvel that is this telescope. That's all for Marcia right after this. But if you have any questions about the science or about our daily lives, we'd love to hear those right now. And again, thank you so much for coming out.
Questions for these lovely speakers?
Okay, we've got a question over here. Yeah, fantastic question. Just to repeat that, yeah. The question was, Hubble did this deep field, where Hubble essentially did a very long exposure shot of a small patch in the universe, which taught us a lot of information. And the question was, are we planning to do something similar? Charity, are we planning on doing something similar?
Yes, in fact, Marcia's team will be doing a deep survey just like that. Here at the University of Arizona, we were awarded a lot of time since she built the camera and everything, so we'll be doing a huge survey. Very similar.
It's called, instead of being called, maybe they'll have another name for it, but it's currently called the James Webb Advanced Deep Extragalactic Survey, or JADES.
Yeah.
So quite a jewel in our collection. Any more questions? Yes, over here.
There's a question from the YouTube live stream. How did you first get interested in astronomy?
We have a question from the YouTube live stream. How did we first get interested in astronomy? Charity, go ahead.
I mean, there's so many reasons, but certainly one of them was how I started my talk, which was, sitting under a night sky and wondering about those fundamental questions that we have as humans.
For me, I had a VHS, an eyewitness documentary on the planets in our solar system, and it took you on a little spaceship and flew you around to them, and it was the coolest stuff ever. It had the best music. You can find it on YouTube. It's 20 minutes. I recommend it. Any more questions?
Let's thank your speakers one more time.
And if you have any more questions, you can come find us. We're around.
Thank you so much. Gosh, that was great. So one thing I neglected to say in the introduction is that, courtesy of Ms. Charity Woodrum, we have a whole bunch of James Webb giveaways over here that are free to you. So if you're now super excited about the science that James Webb is going to do, come get you some swag. I mean, come on. And while you're over here getting swag, you can also purchase a lovely SpaceDrafts sticker for your laptop, for your coffee mug, whatever you want. So we're going to go on a 20-minute intermission. So it is now 7:25. So let's come back at 20 minutes, 7:45. I can do math. 7:45, and we'll continue with Marcia Rieke, who built one of the instruments that's going to be doing this amazing science, so please get excited for that. While you're waiting, please grab another beer, tip your bartender, go check out our telescopes and see what they're looking at, come get you some swag, and we'll see you back in 20 minutes.
So concise. Turns out I'm the second speaker of the evening, and there's an intermission between sets of speakers, so that's why
I'm going to stand up. So the bench doesn't.
I gather it's quiet there. Oh, all right. Hope you had a good time.
Sitting here.
I did. Thanks, Bill. Did you ever see me come running up to take photos? Sit in this corner and take photos. That's how venue for this talk is a place downtown not far from the railroad tracks.
said she's gonna have a lot worse questions for me. Is this your phone?
Where's my keys?
They're behind my.
I wonder if spam pog check.
That's not Annie's area of specialty. Toby might be in the chat.
They were practicing so loudly in the office.
I shut down my email because of saving Wi-Fi space. Okay, there's my email. Or she might send it to the SpaceDrafts. How's my hair look?
Go anywhere without my device.
Hey, that's a good idea.
Yeah.
You got the moon with it. That's pretty cool.
Sorry?
You can look at the moon with it.
Well, okay. I'll just see the spectrum of the sun. But LEDs are pretty well have a good spectrum. They used to have the big deficiency in blue-green, and now they're pretty well
Monochromatic.
pretty well wide line. Yeah, but I can tell from the
Did you learn something?
You were like, yeah, so this one was really different. Oh, it's really bright. Alright.
Sorry, I should have known.
Are you getting ready?
I'm also a graduate student
Nice to meet you. Do you work over the Sky Center? Cool. Oh, nice. For sure. Yeah. It's cool. I mean, we both can't do our job here.
Most people are really excited about space. Who doesn't like to look up and wonder about stars, life in another world, wonder about stars, how they're formed and evolved. So space is really exciting to cover. And having it at a bar, it's a little more lax atmosphere, be a little more casual.
Well, so there's sort of two answers to this. So first is why can you see through dust better in the office? Which is like essentially the size of dust grains are very good at blocking optical light, but not so good at blocking. Sorry, kind of what? Oh, it's but the other question is why can we actually see emission dust? And that's purely a temperature. So the moment you get dust up to a temperature high enough where it would emit in the optical portion of the spectrum, it breaks and it can't survive. And so if you get dust hot enough to the point where you could see it where it would be black body visible light, the dust sublimates and it gets destroyed. They do, but their spectrum is still dominated by light. And so you can still see stars in the infrared. But if you are trying to train your telescope to see dust, again, usually what we do to see something is we compare it to something. Try to create some sort of synthetic color. And so infrared will always have this brighter infrared color rather than but like brown dwarfs, which are stars, those are super good James Webb candidates because those are stars. Our biggest contaminant, some people love them, our biggest contaminant, or we are expected, there's an argument to be made that we might see something that looks like the first galaxy, like in that image you showed there. It could be a brown dwarf, but it's not emitting in the optical, but emits in the infrared. So it looks like it's a there. So we do have to be careful that we're not actually saying that's the most distant galaxy we've ever seen. Well, actually, it's just a brown dwarf. So it pretty much means James Webb will see the most distant brown dwarf ever, but that's
Oh my god, I cannot.
Logan, you were gonna get a duo push because
Okay.
he doesn't want.
Let me get a duo push.
It,
Give me that duo push.
He's pretty mad about.
So did this show up okay, or
It-
you got?
I
Yeah,
cannot see a thing. That light. Oh my gosh. I'm like blind now.
insisted Logan log in. I think this will work.
Perfect. Great.
Thank you so much.
Yep. And now
Thank
it should
you.
show up here.
No, well, no. I'm gonna.
You
So
gotta
you'll
do-
still need to run it from your computer.
Yeah, right. But you
I will-
make it show up.
Yes.
Not on the screen. That's you.
Right. But I thought I had told it to be. Oh, that's not turned on.
I just turned it off.
Ah.
There it is. Okay. So you downloaded it? Yes. And it is a PowerPoint.
Now I understand.
Yeah. We had to do kind of a two-pronged approach because of the live stream. It can't see the screen because it's too bright.
And so we do study.
Okay. Can I do? Oh my gosh, someone has some curry. Oh my gosh, who has curry?
Takes us. So we do a lot of other stuff. So she focuses a lot on dusty galaxies that are nearby-ish, and I focus on those hidden monsters.
Can I make it be in a window like I did with Keynote? How do I do that? Ah!
We're both post-prelim.
Sure, fine.
We're both post-prelim.
Do you know how to do that?
Slideshow.
I was looking in there.
My thesis actually isn't James related. It's related to this one.
I know you can.
Well, we have the internet.
We do. Rolf, do you know how to make it play in a window from PowerPoint?
Just like click slideshow at the top.
Yeah, I was looking in there. I didn't see that.
Setup slide. This says
Setup show?
I'm literally reading this as I.
Browsed by an individual.
Browsed by an individual?
Yeah, and now
That's a weird way to say it.
now click play. Yeah, PowerPoint's.
Browsed by an individual? What a weird phrasing. Okay, let's take this down.
Maybe just replace the window.
No, I'm just gonna do it separately because I have to tell it what window to look at. It's okay. No, this is it. This is it.
Microsoft maybe.
There we go. I'm sure everyone on the live stream is seeing me do this, but I kind of don't care.
Well, I mean it's pointed at.
Yeah.
They're also hearing us talk.
Oh, they sure are. Hey, hi everybody.
It's fine.
It is fine. We are professionals, aren't we? Okay. All right, that should be ready to go.
Fantastic. I'm gonna make it a little. Just right.
Perfect. Don't cover up Marcia though. Okay.
I just
That
wanna
looks
see what.
that looks good. All right.
Cool.
Go. Five-minute warning, everybody. 5 minutes. Grab your beer, grab your telescopes. Be ready in 5 minutes.
Near camp is the name of the specific cabin that Marcia is behind. And I saw that one as well. Telescope itself is just beautiful. Are you working on some kind of operating system these days or not operating at all? No, not Oh, Star Trek. That's optics. Star Trek is platform control, like a geo analysis, all kinds of stuff. Oh, today I had a 30-minute discussion about Zeta analysis. One of the topics today. For another mission, so you and I have some common basis. But I think there's so many people. As soon as I'm making such money, it's very long. That sounds good. And you may pick up some stuff over there. That's just free things you can pick up about it.
All right. Grab a seat, grab your beer. And everybody get ready to our next speaker tonight is Marcia Rieke. Marcia is a bit of astronomy royalty, if I do say so myself. She has built one of the instruments flying on the James Webb, and we are so excited that she has graced us with her presence tonight to tell us all about her journey in James Webb. So give it up for Marcia. Woo! Woo! Woo!
Actually, I'm going to tell you what I've been doing for the last 23 years in rather condensed form, because we started the planning for this mission. The very first thing was in 1996, and I was not part of that because I was busy with an infrared camera for Hubble called NICMOS. And then I joined what was called an ad hoc science working group in 1998 to brainstorm how to build the telescope, what should its outline be, what should its key science programs be, and so on. So let me plunge in here and tell you all about how we build it. You already heard a lot about the science, and I won't dwell too much on this. I'm pointing out a couple of big projects that my own science team is going to spend a lot of our guaranteed observing time on. And Raphael and Charity already described a bit about looking for the first galaxies, and there's one other point I want to make about doing that, where it's absolutely essential to move to the infrared. How many of you know about the fact that the universe is expanding? Yeah, a fair number of you. And that expansion means that galaxies are moving away from us, and the further away they are, the faster they're moving away from us. And moving objects shift the wavelength of the light that they emit. And so when we want to go look for these distant galaxies, the light has been stretched so much that it's moved into the infrared, and in fact, the most interesting ones we want to find, basically, the light has been shifted outside of the range that the Hubble can detect, and therefore we need a telescope that works at much longer infrared wavelengths than Hubble. And do you think these distant galaxies are going to be very bright? No, they're so far away they're going to be very faint, and so that leads to us wanting an infrared telescope, and it has to be able to detect faint things. That means we need a large telescope, and it has to be cold. And I'll talk a little bit more about the cold in a minute. Another thing we want to do that was also mentioned by Charity and Raphael is measure the composition of atmospheres of exoplanets. And the way that we're going to do it is when a exoplanet passes in front of its parent star, what we'll see is the starlight that passes through that atmosphere, and it's going to have some cutouts, some absorptions. And if we look at the pattern of those absorptions, we can tell what kinds of molecules are in the atmosphere. So this shows Webb starts about here, and it can detect all the way out to the right-hand edge of this plot. And so you can see a whole host of molecules: water, carbon dioxide, methane, ozone, and so on. And we're going to learn a lot about exoplanets by using this technique. All right, so let's go down to what large cold implies for how you build your telescope. So here's a guy standing in front of a blast furnace. He's actually holding a match, but you can see it's rather difficult to tell where the match is in this picture because that blast furnace makes such a bright background. I take the blast furnace away, and lo and behold, it's not hard to see the match at all. This is very similar to why we have to cool the telescope. If I turn on my electric stove, but only turn the burner on low, it looks the same as it did when I hadn't turned it on. But if I hold my hand above the burner, I can feel some heat coming up from that burner to my hand. That's infrared radiation being emitted by the warm burner. And so our hand can sense some heat. And if we want to detect these faint distant galaxies, it's absolutely imperative that we cool the telescope, because otherwise all that we'll detect is the heat from the telescope. So we cool the telescope, and that's of course one of the reasons it has to be a space telescope. Because what would happen if we took a telescope here on Earth and cooled it down to maybe 100 degrees below zero? What would happen if we just did that? The atmosphere and water, everything would freeze out on it, and it would be a mess. So we have to go to space, and we need it cold. And the virtue of being a big telescope is not just that you can detect faint things, but you can also see finer detail. So this is a simulation. The top picture, oops, I gotta get my finger just right. The top picture is a galaxy as it would be seen at a wavelength just a little ways into the near infrared with Hubble. It's the longest, I've simulated the longest wavelength that it can see. But you can see that by using Webb at the same wavelength, we can see much, much, much more detail. And so that's another crucial factor. So large, cold, that's what the Webb Space Telescope is all about. And you can see here just how much bigger it is than Hubble. It can collect over 6 times as much light, and that is crucial. And of course, the other important thing is that it goes out to a wavelength 50 times longer than visible light. So, and it goes, much, much further into the infrared than Hubble. You will notice that its primary mirror is segmented, and I'll come back to why that is in a couple of minutes. You can also see over here that it's in an unusual orbit. We actually have sent other satellites to this place that's called the second Lagrange point. And the Earth and this hypothetical point in space can orbit the sun so that the Earth and Webb will stay in the same relationship, which is convenient for sending the data back down. And it's extremely convenient for the keeping cold business, because the sun shield can be positioned so that the moon, the earth, and the sun, all the local hot stuff is all in the same direction. And so it has a virtue that way as well. However, there are some very big challenges in launching such a big rocket, such a big telescope on a rocket. So here is the biggest nose cone money can buy these days. It's actually part of an Ariane 5 rocket, which is the European, one of the main European contributions to the project. It's a telescope made in, you can tell it's late in the day. It's a rocket made in France, and you can see how various parts of Webb stick out from that nose cone. Doesn't fit. So what do? You launch it folded up. And then at the end of September, the payload, the whole telescope spacecraft Sunshield, was loaded on a boat, went through the Panama Canal, and went to French Guiana. And you might ask, why are you going to a former French penal colony with your spacecraft? Well, it's because that is where Arianespace has their launch facility. It's relatively close to the equator, which is helpful, and obviously it's something that the French own. So that's where the Arianespace port is. So here's a picture of what things looked like when the primary mirror was being assembled at Goddard. And each of these black colored places is where there's one of those mirror segments that's underneath the cover and being moved from an area behind here. And then there's an arm that positions them, and the technicians clamp them onto the structure. This is the test facility, the test chamber in Johnson, just outside Houston, and you can see it is enormous by looking at the size of the people. It was originally built to test the lunar rover as part of the Apollo program, so quite a different use. We had to do a lot of refurbishing because this had not been designed for fancy optics that need to be kept clean. This is where you can now see Webb inside the chamber, and up at the top are where the sources are that simulated the stars that we used for the key parts of the testing. And this chamber was evacuated, reduced to very, very low pressure, no atmosphere left, and it also had some special structures, a shield surrounding all this area and some other parts to get the temperature down to what we'll experience out in space. So a very elaborate test. And I have to say, one scary part of this test was that while we were running it is when Hurricane Harvey hit Houston. The telescope was perfectly safe inside this very huge, strong chamber, but those of us running the test had to carpool from the test facility location on the Johnson campus back to our hotels, and there were a couple of times that was starting to get a little scary because they got 50 inches of rain in just a couple days, which is no fun. The worst part was that restaurants were closed and so were grocery stores, but fortunately the people helping run our tests there found some places where they could get us some food so we didn't starve. This shows how the telescope gets moved. It's in this thing that looks like a Quonset hut, and it could just fit in a C-5 transport plane. And then it went on to, as I mentioned, to Northrop Grumman, and this is a partially folded up view. You can see some cables hanging down, and this is the not deployed Sunshield, and these cables all had to be mated so that the electrical lines would go through and the cooling lines for the mid-infrared instrument's cryocooler. Its detectors need to be colder. All that was done. The vibration tests were done. This shows it in the last step before being put back into the shipping container and being sent off to the launch pad. The European Space Agency owns, I think they actually leased this boat that they use for carrying space payloads, rocket parts, mostly from France to French Guiana, but in this case, they went all the way around to Los Angeles and picked up the telescope. You can see the dock here, and this is the just shortly after the boat arrived, but before they actually wheeled the payload out and off to the assembly building. This shows you the full launch complex with an Ariane 5 waiting to be launched. Our launch is not yet, our rocket is not yet moved out to the launch pad. We're still back in one of these, I forget which one of these buildings it is back here, getting ready for launch. And this is what we hope to see the morning of December 18th, 5:20 a.m. Tucson time, and it will be live streamed, I think, on NASA Select, among other places. And I got my fingers crossed, and once we're up and launched, 33 days after, we will turn on NIRCam and we'll start lining up the mirror segments, and I can start heaving a big sigh of relief. Thank you. So do you have questions? Any questions? The question is, does the segmented mirror have the same resolution as a monolithic mirror? And the answer is yes, but if we didn't do anything to the mirror, the 18 segments after launch, we'd see each star 18 times. That'd be useless. So a lot of the first 6 months after launch is spent taking images so that one can line up those 18 segments and get them into an alignment that makes them work as though they were a monolithic mirror, and therefore we get that resolution. Because this would be pointless if we didn't.
My question is kind of a philosophical engineering question. Obviously, this thing might work or it might not work, and how have you consoled yourself to the fact that you might have been doing all this work for 23 years, and any one of a million things could go wrong, and what are you going to do?
So the question is philosophical. How do I reconcile myself to having worked on this for over 20 years and yet it could still fail? I mean, one of the awful things about working on a space project is that something over 1% of all rocket launches result in the thing blowing up. What you do is you don't, you just cross your fingers, fix and control what you can handle, and that which you can't, you hope the other people are doing the correct thing. And I have to say that this mission has been subjected to so much testing and so much scrutiny, and there's been a very, very thorough, detailed test plan that I feel confident that we'll get there. But yes, if you're faint of heart, doing space missions is not a good thing. Okay, holler.
So how long from launch till it gets to the launch point, or wherever it's going to be, before you can actually see it?
It takes about a month to actually get to the Lagrange point, and everything will be fully deployed then, but not yet quite cold enough to start it, which is why it's another 3-4 days before we turn on NIRCam. And NIRCam can operate the warmest of the 4 instruments. And so what the very first job is to find the 18 points of light that come from that one star, so we start the alignment process. So the question is, why didn't we hang out in an orbit going around the Earth for a little while and get the deployments done? And that way, if we needed to fix it, we could. The simple answer is that if we wanted to get something this big to L2, we couldn't use any extra fuel to get us into an orbit circularized around the Earth. We just had to go to L2. And so that had been discussed some long time ago, and it was decided that we couldn't do it because there wasn't a rocket big enough to do it. Where are we going to watch the launch from? Well, I'm trying to get Kathy Duncan organized so that maybe not just the NearCam team, but many of you that work at Steward can be invited to N210 and take a watch.
Very last question, Rob.
When will we see the first images from the telescope?
When NASA headquarters decides we can see them, I'll get to see them right away, but they're not going to publicly release things except on a particular schedule because they're so worried about the press interpreting images before the telescope is acting as a monolith as something wrong. Some of these people are still burned from what happened with Hubble, so they're very conservative, but I bet that we'll release some images before we get everything fully lined up. Bets can be taken in my office.
Oh man, okay, so many questions, yeah.
What target are you most excited about?
The target I'm most excited about is that little patch of sky called the Hubble Deep Field, actually not the northern one, but the southern one that's also called the Extreme Deep Field, or XDF, and we're going to spend a long time looking at that.
More questions? All right, let's give it up for Marcia. All right, thank you very much. This is so exciting. That's it for this evening. I will remind you all to please tip your bartender. There is still some free stuff available over here, so please grab it. And we are still selling stickers. And the Astronomy Club still has telescopes out by the train yard. So feel free to check out the telescopes, grab another beer, come over and buy a sticker, and have a great evening. Oh, and if you saw the gentleman here with the camera earlier, there will be a special about our show tonight on K-Gun Channel 9 at 10 p.m. So you might see yourself on TV. Have a good night. Woo woo! Great job, everybody. Lily, you're amazing. You are a superstar. You're a superstar.
Too bright.
No, we want to start in the
I'm gonna